upon where you are. So today we have the 5-country report plus the IEA HPT introduction, and then I'll give us some quick introductions so that you can hear about our research progress we made over the last 5 years from 5 countries, and then we'll have some discussions after each presentation as well. To begin with, I'd like to introduce Dr. Metkel Yebiyo from the IEA HPT for the introduction of the IEA HPT. All right. Metkel, please go ahead.
Thank you, Yunho. Let me quickly share my slides. Okay, so I think you can see my slides, right?
Yep.
Yes, it's good afternoon, good morning, wherever you are. Welcome again to the Annex 54 webinar. I will quickly provide an introduction about what the HPT TCP is. But before, of course, we start our webinar, just a quick housekeeping. We want to inform you that the webinar will be recorded and will be posted on our HPT Annex 54 website. Please mute your microphone and leave your camera off. And for any technical support during the webinar, you can contact me either in my email or I will be here available. So if there are any technical support needed, I will be available. And if you have any questions, as Yunho said, or comments during the presentations, please write them in the text, and we will make sure they are answered during the presentation. But if the time runs out, then we will make sure they are answered by the presenters. And also, please, we need to avoid to have a parallel discussions in the chat if we can. So my name is Metkel Yebiyo. I am a member of the Heat Pump Center team, and I work for the Research Institute of Sweden as a researcher. So I will quickly tell you about what the HPT TCP is all about, or the Heat Pumping Technology Collaboration Program. Some of you, I'm sure, you know about it, but others may not know anything about it. So the Heat Pumping Technology TCP, or Technology Collaboration Program, is one of the 40 technology collaboration programs which are operated by the IEA. And this particular TCP has been running since the 1978, and it is an international framework of cooperation and network for different HPT actors, or the heat pumping technology actors, and it's also a platform to exchange knowledge and experience. And ultimately, it aimed to contribute to technology improvements by RDD&D, the research, development, deployment, and dissemination projects. And as of today, we have 20 member countries all over the world, China, US. So the members are quite wide countries that we have. So if you look at the heat pumping technologies, what it encompasses, so it includes heating and cooling, air conditioning, and also refrigeration. Those primary 3 areas are within it. And the applications covered, we have residential and commercial buildings, industries, thermal grids in cities and communities, and other applications. And by now, of course, as we all know, heat pump is becoming the ingredient of every aspect that we can think of, whether it is in the sector coupling, whether it's in the positive energy district, whether it's in the energy efficiency. The application is becoming wide. And if we look at the HPT TCP, the organization and management format, we have the executive committee, which are the board of the HPT TCP, and each country has one vote per member country. And then within it, we have the national teams, which are the organizations representing the national heat pumping technology activities. And of course, ultimately, these are the forum for discussion, networking, and creation of new ideas. And the national teams also meet during the national experts meeting. This is a place where we conceive or initiate new ideas for an international collaboration programs. And within the HPT TCP, we have the Heat Pump Center. And this is the center, the central program or office and communication center for all the activities within the HPT TCP. And one of the pillar or backbone of the HPT TCP are the annexes or the international collaboration projects. And these are ultimately to elaborate new knowledge through collaborative research, development, deployment, and dissemination work. And if you look at today's webinar, which is the Annex 54 final results webinar, is stemmed from these annexes or projects. And if we look at the communication and dialogue channels, we, in terms of the publication, we publish results from the different annexes or international projects. We have a prestigious HPT magazine, or the Heat Pumping Technology magazine, which I will tell you a little bit more in the next slide, and also a digital newsletter. We have a website, heatpumpingtechnologies.org, and we're also active in different social media platforms, whether it's in LinkedIn, X, and also on WeChat. As part of the activities within the HPT TCP, we operate, we organize conferences every third year. So for example, last year on May 2023, we had organized a conference in USA, in Chicago, and then the next conference will be held in May 2026, and it will be in Vienna, Austria. And in addition to that, we organize the National Experts Meeting. And as I said, these are the place where we actually conceive all the current ongoing annexes has been developed or conceived by meeting in this National Experts Meeting. So the National Experts Meeting is done once on site, and the other year is online. So our next National Experts Meeting will be sometime in October, and we will communicate the exact date. And in addition to that, we also run workshops and webinars similar to the webinar that we have today, but also we have a member country reports where we invite different countries to share their experience in terms of the heat pumping technology markets and the research and developments related to heat pump. And we also provide support to the IEA publications through the research findings that we have in the different research international collaboration projects. One of the many activities that we operate or we run this prestigious Heat Pumping Technology magazine and newsletter. So this is a digital magazine, and it's a free magazine. So for example, if we look at this year's themes or topics that we plan to publish, the issue number 1 has been released in May 8, and it explored heat pumps unleashing flexibility and sector coupling. So primarily the focus was on flexibility and sector coupling. The next issue would be released in September 6th, and it will look at how to extend the working envelope of heat pumps. So if there are people interested to contribute, whether it is on the topical article or non-topical article, please contact me. I'm the editor of the magazine. So if there are any of you who are interested to contribute or publish, please drop us an email and we can guide you how to do that. And then, of course, the third issue will explore on scaling up deployment with innovative solutions and overcoming barriers. So as I said, it's one of the prestigious magazines that we have in the industry, which are primarily focused on research related to any aspects of heat pump that you can think of. And please subscribe to our magazine, and it's free and it's digital. So you get to know the progress and what's going on within the HPT TCP in addition to that. And these are the team within the Heat Pump Center. We have our chairman, Stefan Renz, Monica Axel, Caroline Hegland-Stigno, myself, and Emilia Pisani are the team. So if you have any questions or if you want to know more information about what the HPT TCP and how the Heat Pump Center operate, we are happy to support and help. And that's me for now. Yunho, back to you.
All right, thank you, Metkel. Do you see my screen?
Yes.
All right, great. Thanks for confirmation. So I'm going to introduce Annex 54, and then each country report will be followed. So Annex 54, we had the following objectives. The first one was promoting the application of the low global warming potential refrigerant to accelerate the phase down of the high global warming potential HFCs. The second was developing design guidelines for optimized component and systems for low-GWP refrigerant. Our member countries are France, Germany, Italy, Korea, Sweden, US, and Austria and Japan. With 8 countries involved in, as you can see below, there are organizations from universities and national labs and the industrial partners. They are all work together for Annex 54. We started from 2019 to 2023, and with the following 5 tasks. The first task was reviewing state-of-the-art technologies using low global warming potential refrigerant. The second task was case studies and design guidelines for optimization of component and systems. And third task was reviewing design optimizations and advancing the impact of LCCP reductions. First task was making an outlook for 2030, and last task was making a report. Since 3 countries are not able to join today, I'm going to make a quick summary of the 3 countries who are not able to join today. The first one was Austria. They conducted charge-optimized R290 systems, and they learned that R290 system can save 18% of the annual energy consumption as compared to the R410A baseline. They also evaluated the LCCPs for 3 different systems, starting from the R410A baseline, and then charge-optimized R290 system, and then natural gas heating system. Charge-optimized R290 system was able to save about 87% of the total emissions as compared to the natural gas heating system. That was one of the findings. The second country is Japan. Japan conducted many different tasks, including review of the regulations and state-of-the-art technologies. The second was investigating low-GWP residential and commercial systems utilizing HFO 1123 and HCFO 1224YDG. And also they conducted risk assessment of A2L refrigerant. And then last task was evaluating LCCPs for air-to-air heat pumps using next generation refrigerant. Third country was the Korea. And then Korea did R32 AC development for window air conditioning application for the US market and split ACs for European market. They also conducted literature review on the application of the low global warming potential refrigerant for high temperature heat pump. As you can see from this chart, they conducted several tests at rated conditions, and they reported that the heating capacity of R32 was about 5% higher, while the COP was about the same. So those are the quick summary about the three countries' effort. In summary, we explored state-of-the-art technologies using low global warming potential refrigerant, and we presented many case studies for optimizing component systems to reduce the refrigerant charge and improve their LCCP. And Asian countries and US favor HFC and A2L HFO HFC mixtures. Of course, their global warming potential was lower. And the next is Europe. And European leans towards the natural refrigerant like hydrocarbons and CO2, so that you can hear many of these projects. Overall, the comprehensive report from these countries emphasize the global push toward adapting lower global warming potential refrigerant. The collaborative development of safety standard and system architectures for flammable refrigerant will advance sustainable HVAC technologies, significantly reducing greenhouse gas emissions. Some suggestions are by the regulations, low global warming potential refrigerant will be used in the coming years. To accelerate these transitions, the safe use of flammable refrigerant, except for CO2, must be supported. With this, as safety aspects are the main target of the new study Annex 64, led by Professor Bejan Palm. Other suggested research topics are minimizing the charge and designing such component like a compressor and heat exchangers, and developing mitigation method for leakage cases, such as developing refrigerant sensors, shut-off valve, and dampers, and then developing new cooling and heating system architecture that will allow flammable refrigerant or A2L or A3 refrigerant, and developing FDD technologies. Those are our suggestions. And one last announcement is that at the University of Maryland, the USA College Park will be organizing next 16th IIR Gustav Renton Conference on natural refrigerant, so that all the participants today's Zoom meeting webinar are invited for this event. So the date is August 11 to 14. Registration site is open, so please join us. So again, my name is Yunho Hwang. I was serving as an Annex 54 operating agent. And if you have any questions, please use this email for the contact. And also, if you have any question on the IEA HPT, then please contact Caroline or Metkel. And their emails are written here, so please refer that. So with that, then I'd like to start our country report. The first speaker is from France. Okay, let me make sure Julian is here. Okay, Metkel, do you see Julian?
No.
Okay, if not, then we'll be moving to the Germany country report. From Germany, we have two speakers. The first speaker is Theodor Altersdorf from Fraunhofer, and followed by Christian Beuring from AN University. So Teodoro, please go ahead. Yeah, Teodoro, you are muted. Please unmute yourself.
I should share my screen, or will you share the slides?
Yeah, please share. Yeah, please
Yes,
share your screen. Yeah.
Yes. Just a moment. So, can you see the presentation or the presenter mode? Okay.
Yes.
So thank you everyone for attending the final meeting today, and thank you, Yunho, for all your efforts you have done for the operating agent. So today I show you the situation of low-GWP refrigerants for Germany. So I will start with the development of projects being done in the energy research sector for Germany. Since some years, we have the so-called Enargus database available, at which all the energy research projects which have been funded by the Federal Ministry of Economics and Climate Action, where they got funding in the past and still get funding. And I analyzed the whole database to get to know what's the current situation for projects that have got any funding. So that means all these projects, what you see is just projecting or giving an overview about the situation for the publicly funded projects, and this is not private actions from any companies. So what you see here is actually the development of this process. So please do not ask me why this development of the budget looks so linear in the beginning. So overall, it can be stated that until now, until the beginning of 2024, there were about 65 million euro being publicly funded for projects which have been related to refrigerants since 1978. And I did an analysis on all the data of these projects which were natural refrigerant projecting, or which were looking for F-gases. And as you can see in this green curve, that the amount of projects, it's about 78 projects with state of today or state of 2024, which have been related to alternative or natural refrigerants. And the F-gas projects, they stayed at a relatively low level since 2017. It is always important to have an idea about the situation of the market. On one side, on the supply of heat pumps, but also on the demand side. And we tried to gather the knowledge, gather the data together. What is the supply side? So this is relatively easy. There are a lot of product databases available, which can be analyzed just by the type of refrigerant which is used in these models. And what you see here is actually a bar plot of the product data of the heat pump KeyMark database. This is also a publicly available database. And if you have a look on it, all the heat pump models, this is not distinguishing between the different types. This is just a survey in all the types together, to have an idea what is the how the supply side of heat pumps being offered on the market develops since in the last years. So that means in the project, in the duration of the Annex 54, we did three different we took three versions of this database, because this database is always developed continuously. And we just made a snapshot at these years and filtered it. And as you can see, the amount of heat pumps that are using low-GWP refrigerant is significant, much more significant for R32 compared to R290. It's not so large for the other low-GWP refrigerants like R513A, but as you can see, the demand side is dominated by the low-GWP refrigerant R32. The supply side is, as I said at the beginning, is only giving an overview about what's offered on the market, and it is not rating what is the operator or the owner of the system. What do they want when they buy new equipment? And this, of course, is usually quite difficult to get these data. These data are scarce. Usually, these are data from associations or from companies. And we have the lucky situation that from the funding program, we got the possibility to analyze the data of the German heat pump funding program. And what you see here is this funding market of heat pumps. So that please do not try to project this share or this information on the real sold unit numbers for heat pumps, because this might differ a little bit. Because when you have a funding application, that does not mean that you have installed and commissioned the system at the same year. This can be done in the next year. So for this reason, this might differ from real sold units a little bit. So, and as you can see here, the situation looks very different. The dominating refrigerant in this graph is still R410A. So R410A in the last 4 years, since 2020, it got a lot of large decrease. And this decrease was a transition, a shift from R410A and from R407C towards R32 and R290. So you can see it's a quite good development and quite stable development for R290 since the last until the last year. And you see here in the last year there was a drop. There was an increase in 2021 and in 23 for R32. And we talked to some industrial actors, to some manufacturers, and most of them agreed that the main reason for these are supply issues for certain components for R290 systems in the last year. So, and this gave, this was the main reason for this increase of share in R32 systems. Now you have at least some overview about the current situation on the supply side, on the demand side for heat pumps in Germany. Now I come to an SCP analysis, which was done in the project duration from Fraunhofer. Here, this SCP analysis has a look into the current situation from today. It was in 2020, so it's already 4 years old. But here we compare just gas boilers with 4 different heat pumps, some general heat pumps from the market. And well, what you can see is that what can be stated is, of course, it is most crucial that in this transition to renewable heating, that heat pumps is deployed and not what kind of refrigerant is being deployed. So this, I think, is the main fact we should follow overall. But what we can see in the last 4 years is, or in the last 10 years, I would say, the energy mix for renewable energy resources for the electrical energy grid is also shifted and transitioned fast into the direction of renewables. And when this comes into play, it is also interesting to see how the reduction or the potentials are distributed between deploying still R410A or R32 or R454C or R290. And as you can see, the more renewable energy is part of the energy mix, the more this change will give a difference. So that means the indirect emissions are decreasing, of course, because of the electrical energy, and the direct emissions or the emissions from production come more into play. So what I haven't said in the beginning is that here you see 2 different versions. You always see version 1 and version 2. what I want to state here is that this is due to this uncertainty you have for the global warming. You could still say we deploy global warming potentials, which are very often used as political in legal constraints and legal frameworks, as from the IPCC assessment report from 2007, or you can also go for the situation of the newer global warming potentials, which were as part of the state of the art from sciences, has increased for most F gases overall. So and not only this, also the degradation effects which can come into play, well, not for these refrigerants, but this also would put some changes for global warming potentials. So this is the reason why you see these version 1 and version 2 always in this graph. So and based on this, you can see that R290 is the best option for heat pumps overall. So, and yeah, of course, I would say most of you are not surprised from these results. And when you, yeah, I want to present also some final findings on the RC150 project. In this project, we at the end we projected to have 40 different tested prototypes, but at the end, with all the issues you have during setting up laboratories, setting up prototypes, at the end we tested 24 different prototypes, different combinations of heat exchangers and newly developed compressors for R290. And each of the prototypes was tested at 20 different operating conditions, between 8 to 20 different charges to identify what is the optimal charge of the system, so that overall, with all these 24, the permutation of all these 24 different prototypes and all these operating points tested, we had more than 8,000 different tested operating conditions. And at the end, we rated these systems based on a typical operation condition for brine water or ground source heat pumps in Europe, which is the heat source temperature of 0 degrees Celsius and the supply side temperature of 34 degrees Celsius and the superheating of 10 Kelvin, and the compressor frequency at 100%. And based on this, these results were, or based on the optimal charge, you can see what are these 24 different prototypes has been tested so far. So that means we were able to reach about 12.8 kilowatt heating capacity with about, I think it was between 2 different prototypes were able to get it. And we had, I think, 180 and 240 gram. And in this range, these maximum prototypes has been tested. So actually, the red area was what we projected at the beginning of the project, what we want to reach, and we at least exceeded it a little bit. So this was a very glad and lucky situation. So conclusions on the country report or for the German side is that a very diverse research takes place in Germany since 2012. A lot of projects have started, especially for natural refrigerants. But I would say efficiency and safety are some key actions or key topics which are followed in this research. Well, the application range is quite broad, so it's not only all these projects I filtered in this Argus database is not only dealing with heat pumps, of course. This is also dealing with other appliances using refrigerants, so tumble dryers, thermal management systems for electric vehicles, hybrid and absorption heat pumps, and of course, most of the projects are vapor compression systems. So you will also find in our final report, which I have not presented today, but because you can find it at diverse other references, is the field test analysis. And in this, you will find all the carbon dioxide avoidance potentials and reflecting changes in the energy production emissions just based on deployed heat pumps. And the funding market analysis, we think this is a very important analysis because it gives you insights into this development, and we hope that that these data can contribute to to ensure yourself or to ensure someone's mission, how to say, what should be deployed for refrigerants in the future. So I think everything is written here. You can read it afterwards. Actually, it's more or less the same as I said before. Yeah, well, the last bullet point I would like to add here. So when these data, about 30 European-based manufacturing facilities were analyzed for the production capacities. I don't know who has followed this change of the F-gas regulation in March 2024. There was a lot of discussion before this date that production capacities might not be enough for R290 refrigerants, and we should go for all refrigerants. We made an analysis with a lot of insights into the production capacities of 30 different European-based manufacturing facilities. And the data which were published usually just have a general look what refrigerant heat pump production capacities are, and they have not had a look into the refrigerant-specific production facilities. And we can state that just for the air-to-water heat pump market, right now, there won't be any future issues in terms of supply issues. So that means it would be easy to go for the air-to-water heat pump market and flood it actually with R290 heat pumps right now. So, and the outlook is in R&D projects as analyzed. We are aiming for usually for prototype level demonstrators with a close link to high technical readiness levels, the large amount of still ongoing projects and the high share of projects aiming for non-halogenated refrigerant promises technologies for several device classes, but with a clear focus on heat pumps in several sectors within the next 2 to 10 years. Charge reduction and safety technologies in conjunction with each other will lead to safer heat pumps for single and multi-family houses when ongoing R&D projects are finished. So we would say that in 2028, the spectrum on multi-family house heat pumps will be as diverse as it is in air-to-water heat pumps right now. So that's what we can forecast from the ongoing development activities we see. Establishing safety performance testing. Greetings to Daniel Coburn. It's a term he has defined in the past. I like it very much. Will lead to more knowledge, more reliable, as well as more standardized testing to deal with flammable refrigerants, satisfying the safety demand of the heat pump market. So, and market data will be further analyzed to improve benchmark data sets, as well as to allow more thorough market analysis in general. So thank you very much for your attention.
All right, thank you, Teoru. For the audience, please use the chatting box for your questions, then we'll try to read it and answer back to you. Meanwhile, you are preparing for any questions to Teoru. We have a second speaker from Germany who will be speaking about the progress again. He's a Christian Behring. So Christian Behring, please prepare and upload your slide.
Hey. So you see my slides, right?
Yeah, it's coming, but then yeah, okay, we can see it now.
Perfect.
Great, thank you.
Yeah, thank you for your kind attention, and let me welcome you all from Aachen, Germany, and let me talk about low GWP refrigerants in heat pumps and what we did in the last years in Aachen to capture this topic. What you will see in the end is an ecologic assessment of heat pumps, which is part of the final report as the last part that we state in the outlook. So a brief introduction. Let me start with my team. I'm Christian. I'm the team leader of the team refrigerant cycles, and we try to build the even best thinkable heat pump cycle from the molecule to the operating strategy, and we integrate different methods to do so. So we start with refrigerant selection. We tailor the refrigerant cycle, design the components, design the controller, and then we go in optimization of operation. And finally, we have the system that we want to integrate into our energy system, basically. Since we are from the Institute of Energy Efficient Buildings and Indoor Climate, our main focus is on buildings, but recently we shifted towards industrial processes as well as mobile applications. The heart of our team is the experimental facility, which is called the Refrigerant Lab, in which we implemented the field test in the lab concept, and we handle herein flammable refrigerants in a fully automated manner. So we are able to emulate dynamic test conditions, which follows the hardware in the loop principle, and we have dynamic boundary conditions for source and sink side. This is an entirely safe test environment handling A3 refrigerants, and we have an exhaust air system that helps us identifying and getting rid of concentration of flammable refrigerants. This test center is able to be operated 24/7, so we are able to conduct experiments in a very well manner. The test benches are a compressor test bench, an expansion valve test bench, a brine to water and air to water heat pump. And using, for example, the brine to water heat pump, we are able to measure different refrigerants. We assess their performance, and then we are able to implement their behavior into simulation models. And what we simulated recently, we did a life cycle assessment for the heat pump, and then we compared the heat pump to a gas condensing boiler under boundary conditions in Germany to assess whether we're getting better from an ecologic point of view or not. Life cycle assessment is a well-known method that is applied to many applications in the literature and in practice. And this is our model that we implemented for the life cycle assessment of heat pumps and gas condensing boilers. So we have input data taken from EcoInvent for materials, electricity, heat, and chemicals. They go into the heat pump production and the refrigerant production. Then we have a second phase, the heat pump operation, which is about 18 years providing heat to a building. And during operation, we have leakage. And on the right-hand side, we have recycling for heat pump and refrigerant, which is not part of the study. This is something we are recently researching, and we investigate in this in Annex 65, where we have circular economy of heat pumps. So let me go further. We have different models here behind it. We have a heat pump production based on the materials and the energy intensity. We have the refrigerant production based on chemical equations. And then we have the heat pump operation based on the assessment of the refrigerants in our lab and the heat that is necessary to provide a building. And what we find, electricity has the biggest influencing factor on the ecologics of heat pumps. The heat pump efficiency is the most important evaluation criterion, and other life cycle stages only as a secondary influence. How can we see this? Let me explain this graph. We have environmental impacts normalized to 100% as the baseline. So a heat pump with R14A is our baseline case. And now we have the assessment metric climate change. And by changing the refrigerant, for example, to R32 or to R717, reduces our climate impact here. This is assessment in equivalent CO2 emissions, but we can do it for all other 16 OECD metrics that are part of an entire holistic ecologic assessment. And now we can distinguish between leakage, operation, and production. And what you see here, when you have a fluor molecule in our bondings, then we have parts of leakage that account for climate change, for example. Or if we look at particular matter formation, the use of R717 has a slight impact here. But in all, we see the first point, the influencing factor is electricity, because most of the parts of our environmental impact is related to operation, and operation is related to electricity. Then we have heat pump production here in the end, which accounts for material resources. For example, the R717 here does not need copper because it would attack copper more or less. So the impact of not using copper is quite large compared to the other refrigerants in heat pumps. And how could we reduce it in Germany? At least for the operation part, we could reduce the CO2 emissions in our electrical grid, or we can increase the heat pump efficiency because this is the largest lever for the heat pumps. Before we have questions regarding ozone depletion, let me say one thing here. We have ozone depletion for R410A, R32, and R1234YF due to the production way we implemented. So based on the chemicals we have in the production, we have leakage assumed in the production, and this yields ozone depletion. This is why we have these three blue bars here. The other yellow bars are all related to operation. So we got through these points, and now the comparison to gas boilers. If we apply the GE grid mix, which is from EcoInvent again, we see that at least in 4 categories, we are already today better than the gas condensing boiler. We are better in climate change, ozone depletion, photochemical ozone formation, and energy resources. In the other categories, it's getting worse. So this is a finding for research. We don't know yet if getting worse is bad for our environment or not, but this has to be assessed by other guys. In the long term, we assume that we have an improved grid mix, and the improved grid mix, the SDS grid mix, for example, improves climate change for up to 80%. And now we see, if we look into our future, we are better in at least half of the categories from an ecologic point of view. There are still some categories like human toxicity, non-cancer, or material resources, where it's quite red. And in addition, for land use and water use, the land use correlates to the photovoltaics and the wind turbines we need to make this electricity mix. So these are points that we cannot avoid today. And this is called burden shifting. So we changed the technology to heat pumps, and it's getting worse in some categories. So we have still some work to do to solve all these problems in the long term. And this is the findings that we integrate into the report. We see the electricity demand is the main influencing factor. Today, the greenhouse gas emissions will be improved by switching to heat pumps, but we saw burden shifting towards other environmental categories. And now our target is to investigate which categories are very important. That's the first. And the second, we have to include the recycling process to see which impact this has on the overall assessment. Thank you for your kind attention. The slides will be uploaded in the end, and I'm looking forward to your questions. Thanks a lot.
All right, thank you, Christian. There was online questions. I'm going to read it for you. Also, you can check it from the sharing box. The question was from Harshad Inamdar from RIM. He's asking 2 questions. The first one is, if you are not using copper for R717 heat pump, did you consider another matter like a stainless steel?
Yeah, thanks for the question. Very good observation. For all refrigerants, we use a mix of, I guess, 25% copper, and the rest is stainless steel. And for the R717 heat pump, we used only stainless steel as in exchange for copper. The details of the studies are in our heat pump conference paper to life cycle assessment. So there you see the detailed model of the shares of materials that we implemented. All right.
His second question is about LCCP, or environmental impact analysis, related with the refrigerant leakages. The first question is, what was the annual leakage assumptions? And the second question is, what was the heat pump lifetime?
Yeah, I can answer. For our studies, it was 2% per year.
And then lifetime of the heat pump was?
18 years.
Oh, 18 years. Okay, same question to Hyoru. What was your assumption on this?
Our assumption was 15 years and 3%, I think, but I need to have a look. Give me 5 minutes. I can say it later. I will write it in the chat. Just a moment.
Okay, yeah, that'd be great. All right, thank you for your presentations. If you have any questions to join and report, yeah, please use the chatting box to asking questions. All right, our next speaker is Julien Ballot from CETIAT. He'll be making a presentation on France country report. So Julien, please upload your slide, and it's all yours.
Thank you. Yes, sorry for the delay. Can you see my screen?
Yes, please use the presentation mode, please.
Yeah, sure. Okay, wait, it's on the wrong screen. Okay, I will just share that. Yeah. Okay. Okay, now you can see the good screen.
Still the same.
Wait, I will.
Maybe use the swapping the screen.
Yeah. So now, yeah, it should be this one. It's good now. It's it for
Yes, good
screen.
enough. Yeah, please go ahead.
Yes, sorry for that. So I'm going to talk a little bit about CETIAT work on for Annex 54. So we had a project on low-GWP refrigerant, and it's ending this year, like in a few months. So lots of different things were done in this project, and a few things were and some things were shared with the Annex 54 for the Annex 54 work. So I'm going to talk about 3 studies. The problem is that the first 2 of them, I wasn't there when it was done. It was done by a different person, so I will not be able to answer a lot precisely to question about those 2. And for the third one, again, problem of schedule. I only assisted some of my colleagues to do this work and those tests. So I will not be the best person to ask a question, but I might have a few answers. And anyway, I can share them the question, and they'll be able to answer you later. So sorry again about that, and I will now begin. So the first study shared to the Annex 54, it was done a few years ago, 2019 or 2018, and the idea was to compare a few possible candidates for dropping replacement concerning several refrigerants. And so the idea was really to run a lot of performance tests just by simply changing the refrigerant and then monitoring the different results. So yes, the idea was not to change anything in the components of the heat pump, and just to optimize the charge and to check the thermal performance of the heat pump with the new refrigerant used. So for this study, it was two type of heat pump were used. So one air to water heat pump and water to air heat pump, and also there is one so 3 types, sorry, one heat pump water heater. So the idea was to make standard performance test. So based on the EN 14501 11, sorry, and so for nominal performances, and the other one for domestic hot water performances. So the idea was just to follow a strict test protocol. So first, there was some study made on what possible candidates could they find to replace the R410A. So they selected those 5 refrigerants. So all of them are mixtures except for R42. So yes, the study is becoming a bit old, but that was what that was made a few years ago. The idea was to test both cooling and heating mode in for different conditions, and to run a lot of different tests. All the different results. So maybe if that interests you, you can see in the France country report that my colleague made when these studies summed up. So in the end, I think what stands out is the R42 and also maybe the R454B. And then for another kind of heat pump, so this time water to air, it was the idea was to test a replacement candidate for R407C. Yeah, so I think result that we all know today is that most of the refrigerants are flammable now. So this is a new issue we'll have to deal with. So the same kind of results were made. I'm going to go a bit quickly on those studies because if they interest you, you can check on the reports. And then the last one was to test a heat pump water heater. So the overall conclusion of this small study was first to use the R42, but then it's become a bit old, and several candidates were founded to replace R407C and R134A. A second study was made also before 2020. This time it was to study the heat transfer on a thin and tube heat exchanger to see how it was possible to improve it using different refrigerants. So this time it was a study conducted in 2 steps. So first step was to use the EvapCond software to find the candidate that suited the most the thermodynamic cycle that was used. And then there were some tests that were carried out on thin and tube heat exchanger, so in both evaporation and condensation mode. So as you can see below, it was made by some colleagues that are not working in CITIAT anymore. For some of them, they retired. But if you need to have some information about that, we can give you them afterwards. So the idea was to compare the properties of the different refrigerant to find the best candidates that will involve the less changes. So that's some results for the condensation mode. So that was the the properties that were used with the software, and that's the same for the evaporation mode. Then the idea was to, with the tests that were made, to check if the calculated capacity was relevant concerning the tested the actual capacities. So what stands out, it was really quite good. Like there was good accordances. So the main conclusion, overall idea of this study, I think, is to just say that it's quite convenient and useful to use some software to find the refrigerant with the property that interests you, and know even yeah, and know you can have some good results. Yeah, so that's the overall conclusion, and there is also a small point at the end to say that during the test they found that they had like not good enough performances with R32. So this could be dealt with like a better design to really adapt the evaporator to these fluid properties. So using R42, for example, as a simple dropping could be like a temporary solution, but not ideal. So yeah, that concludes the first two studies that were shared, and now some of the last one that was made last year. So after those studies, there were some other things that were made in this project led by CTAT. The idea was to build 4 prototypes of heat pump using low-GWP refrigerant. And the idea of building 4 prototypes was for each prototype to study one particular question. So for this one, it was the second one built. It's an it's a water-to-water heat pump. The idea was to find the minimum, was to reduce the maximum, the refrigerant charge. So this one used propane, which was found to be the most promising candidate because, well, the GWP is minimum. The only issue with propane is flammability, as you know. So one of the first easiest way to deal with flammability is to reduce the maximum the amount. So the idea was to design a prototype that could be similar to like a domestic heat pump for single houses. The water-to-water choice was made because for minimizing the charge purposes, and the idea behind it is that you can maybe add an air to water heat exchanger to use it afterwards. So here on this prototype, there was a few parameters that were studied. So first, the influence of superheating and of the compressor speed. And also there were a few tests on the components because there were 2 compressors that were used, and also a few different condenser and evaporator. And in the end, they also succeed to make some seasonal performances analysis. And yeah, so you can see in the picture the prototype that was designed and built in CTAT and tested in CTAT test chamber. So that's the overall principle of the heat pump. So as I said before, the idea was to use an external heat exchanger, so air to water, so that it can be considered as maybe air to water heat pump, but with a very small amount of refrigerant inside. So that's the test condition that were chosen. So there were several, so two compressors chosen. First, a rotary compressor, and then a scroll one. There is also there were the idea to use an automotive compressors, so like a really small one designed for to be used in cars, but in the end the performance weren't that good, and I think we also had some issue to control it properly. So this is it was an interesting idea, and maybe it could be developed more, but in those tests, for those tests, it doesn't really stand out. So first, there was some charge optimization that were made, and different superheating temperature were tested, and you can see so then the influence of superheating on the performances. And also, one interesting thing is that there is no point to reduce too much the superheating. And then on the right side, you can see the impact of the compressor speed. So as we were working here with some really low charges, it didn't really seem to have like a big influence, but maybe also because those compressors used weren't completely designed to work with this amount of refrigerant. And also, if I remember well from the test, there were lots of issue with oil and too much oil in the whole circuit. Then some other components were changed. So we used plate heat exchanger for the both condensation and evaporation side. Of course, the idea, if you reduce the size of the evaporator, you will have less charge, but also less performances. So then again, an optimum was founded, and the idea also was to try to have as minimum component in the circuit. So I think we for this one no liquid receiver were made. It was only test with in heating mode, so no reverse cycle. So the idea to have a condenser that is a bit bigger than what's really needed could be interesting to remove the liquid receiver. In the end, they made some seasonal performance tests, so like 14825, the European standard. So what stands out is that the configuration, of course, with the most with the bigger charge performed better, but it's also interesting to see that if I remember well, yeah, the configuration 4, it was with the automotive compressor, and the 3, it was with the other one. it's also not well, there is nothing to be ashamed of, and it's like twice the half of the charge. So that's quite interesting, and I think the overall conclusion of this study was that with the proper design on the components could really achieve like good performances with really small amount of propane. So in the end, there is only one configuration that really didn't work. It was the second one. So if I go back, the second one, it was with the biggest evaporator, because then you cannot simply you don't have enough refrigerant to have like the proper heat transfer and so on. But on overall, like they all work pretty good without, and the optimization and the design also was not that optimized. Well, the things that were optimized is to choose some components that were quite small and quickly available with our industrial partners. But yeah, there were no special design of components for those prototypes. So that's quite encouraging results. And I think, yeah, so that's the overall conclusion. So maybe the first two are a bit dated now, but the idea is that there are lots of dropping replacement solution that can be used to change now some refrigerants, especially some mixtures. Mixtures can be really interesting and have really interesting properties, and those properties can be in a way easily studied, and also in a quite relevant way by using some software and simulation tools. And with I don't say it's easy, but with some optimization on the components, you could really achieve some pretty good performances using small amount of propane. And I think for other flammable refrigerant, the question could be the same. Yeah. So that's all for me. Sorry for this presentation, because I don't have all the information in my mind right now, but they can be found. And if you have some question, I'll try to answer them. And if not, I will write to my colleagues for that.
All right, thank you, Julian. The meanwhile, Theory answered for previous questions about the LCCP assumptions. His lifetime assumption was 15 years, and annual leakage rate was 3%. Theory also write detailed answers so that you can take a look at the chatting box for more details. If you have any questions to Julian, again, please use the chatting box so that we can read it and answer in the next round. Our next model is Italian country report. Three presenters will make a presentation. Those are Sergio Poppa from the CNR, and Marco Azzoli from University of Padova, and Luca Molinari from Politecnico University of Milano. So first, presentation will be given by Sergio, I think, as shown here in the slide. So yeah, please go ahead.
Okay, can you hear? Can you see my screen?
Yes.
Okay, so thank you, Yunho. Good morning, afternoon, or evening, everyone. I start with a brief introduction about our country report, and then I will let Sergio to go on. So as Italian team, let me say that we are three different research institutes, National Research Council, Politecnico of Milano, and University of Padua. And we were involved in several researches about low-GWP refrigerants. And the researches we carried out span from fundamental studies such as the assessment of refrigerant thermophysical properties and the assessment of the performance during flow boiling and condensation, basically the heat transfer coefficient and pressure drop measurement. And on the other side, we carried out also researches about application, such as the assessment of the performance of low-GWP refrigerant in drop-in application in a lab environment, similarly to what the CETIA did. And also we we were again involved in activities related to the monitoring of pilot plant in which low-GWP refrigerants are used. We are also actively involved in simulation studies, but we don't have time to show you the results. So the first research line we are going to discuss is about the refrigerant thermophysical properties. So please, Sergio, go on.
Okay. Good day, everybody. Thank you, Luca. Yes, I will start with the presentation of our institute. I belong to the Construction Technologies Institute of the National Research Council in Padua, Italy. And our group is devoted to the study of refrigerants, and both from the thermophysical properties point of view and the applications, developing methods, systems, components, and materials for air conditioning and refrigeration. In the last years, we were involved in 3 projects. 2 of them are finished, 1 is still in progress. The two projects already finished are an European project, therefore Civic, that was devoted to the study of the application and development of geothermal heat pumps and the study of the ground heat exchangers. The second project was a bilateral project with the National Research Foundation of Korea and was devoted to the study of heat pumps, but now I will discuss about it. The third project, still in progress, that will finish on 2026, is an European project, ECHO, devoted to the development of an efficient, compact, modular thermal energy storage system involving a heat pump to support the thermal energy storage system. So please, the next slide. As referred, the bilateral project with the National Research Foundation of Korea, our activity was divided in 2 parts. The first one was devoted to the measurement of vapor-liquid equilibria of 2 different mixtures formed by isobutane and 2 HFOs, that is 1243ZF and 1234YF. We measured the vapor-liquid equilibria at different temperatures and regressed the coefficients for the equation of state to calculate the properties of these mixtures. And the second part was performed by us in the laboratories of the University of Seoul, the National University of Seoul, and we tested one of these mixtures, actually the isobutane plus 1234YF mixture at the azeotropic composition in a laboratory heat pump to evaluate and compare its performance with our 134A refrigerant. And the results were quite interesting because the COP of the isotropic mixture were practically the same as those of R134A. And this is obviously a potentiality for the substitution of this fluid, because the mixture studied has a very low GWP, as it is required by the necessity to reduce the global warming. So this is the first project. I will discuss the second project at the end of the presentation of the Italian group. Okay, thank you.
Okay, thank you. Now about the flow boiling and condensation performance. Please, Marco, go on.
Hi, can you hear me?
Yes.
Okay, so good morning and good afternoon. I want to introduce myself. So I'm Marco Zorin. I'm a researcher at the Department of Industrial Engineering at the University of Padua. Before going ahead, I want to say that these activities, the activities that I'm going to present, have been carried out by the Sustainable Thermal Energy Technologies Research Group, in which, beside myself, there is Professor Davide Del Coy, Professor Stefano Bortolin, and Dr. Arianna Berto. So our activity has been mainly focused on the heat transfer, two-phase heat transfer of refrigerant mixtures, in particular in-tube condensation and flow boiling. So the slide that you will see later are related to these two topics. But we were also involved, we also performed some experimental numerical studies of a carbon dioxide dual source heat pump. This heat pump has been realized to work with two evaporators, one air source evaporator and a photovoltaic and thermal evaporators. Okay, so in this way we can exploit air source and also the solar energy as thermal sources for the evaporator. I would like to say that the results of this activity, if you're interested, will be presented at the next Gustav Lorentzen conference at the University of Maryland. And also we were interested in study dual source heat pumps with air and ground as thermal sources. And in this case, we study in particular a heat pump that works with micro-channel heat exchanger as condenser and as evaporator to reduce the refrigerant charge. But now I will show you some, give you some details regarding the heat transfer activity. So we know that we would like to have reliable tools for the design of heat exchanger. And this is important, but to do this, we need to have some experimental database. It is also interesting to see that in some cases, new refrigerants are non-isotropic mixtures, which means that during the phase change, there is a constant pressure, neglecting the pressure drop, but they present a temperature glide. Okay, so it is a gliding temperature process. To study the two-phase transfer, we have some experimental test rings. They are two in particular, depending on the heat flow rate. So we have a bigger loop to study small heat exchangers or channels with 8 mm diameters, and a smaller system to study the heat transfer inside small diameter channels, 1 mm and 3 mm. Now I want just to show you in the next slide a layout of one of our loop. It is a pumped loop, so there is no compressor, there is a pump. And here in such a loop, we can study the heat transfer. What does it mean? It means that in this experimental apparatus, we have several test sections, okay, to measure the heat transfer coefficient, the local heat transfer coefficient of the refrigerant. So here we are not characterizing the whole heat exchanger, but we are just focusing on the refrigerant refrigerant side heat transfer coefficient. Beside measuring the heat transfer coefficient and the pressure drop, in some test sections, we can also visualize the flow pattern. Why? Because to visualizing the flow pattern, we can have a better understanding of the physics of the process, and also because most of the models available on the literature are based on two-phase flow pattern maps. This means that if we want to improve the models, we need before to improve the flow pattern maps. So it is particularly interesting and important to see the flow during this the process of the two-phase transfer. Regarding the condensation studies that we carry out, we focused on HFC and HFOs mixtures. These are the different mixtures that we studied, and because we want to have different thermophysical properties and different temperature glides. So, for example, you see that and in the report there are the details, but we studied some zeotropic mixtures made by R32 and R1234ZE, okay? And in this case, depending on the mass composition, the glide that we studied, it is from 7 up to down to 3 Kelvin, the temperature glide. We also studied the non-flammable mixtures R450A and R515B. These are two mixtures mainly made by R1234ZE. And in this case, they are classified as A1 by the ASHRAE. The glide, it is negligible, so R515B is a zeotropic mixture, so the glide is close to 0. And R450A, it is a near zeotropic one. The glide is very small. We also study other two mixtures made, both are made by R1234YF, and they are the 513A and the 515A. So the heat transfer database that we have developed with these experiments has been used to test and to check the results of different correlations, but I want also to say that this database can be used to develop future correlations or futures model based also on artificial intelligence tools. Yes, this is the last activity regarding the flow boiling. In this case, we have considered these two fluids, R455A and R452B. These two different mixtures have a very different glide. In one case, we have 11 Kelvin of glide, and in the other case, we have about 1 Kelvin. So to study these two refrigerants, it was particularly interesting during flow boiling because here we have the effect of vapor quality, saturation pressure, the heat flux, mass velocity, and the channel diameter, because we tested also these two mixtures in the 8 mm and the 1 mm channel. We have seen that in this case, regarding the transfer coefficient during flow boiling of the refrigerants, the models developed for pure fluids must be corrected to take into consideration the additional mass transfer resistance. This additional mass transfer resistance, it is related to the zeotropic behavior. So it will be much more important when the glide it is 11 Kelvin compared to the case of 1 Kelvin. But in both the cases, we need to correct the heat transfer coefficient of these refrigerants.
Okay, thank you, Marco. Now I will go on with the research at system level. The research at system level was carried out at Politecnico di Milano in the HVAC research group. And basically we carried out two different activities. The first one is the assessment of the energy performance of a heat pump working with several low-GWP refrigerant in entropy application. And the second one was a simulation study carried out to compare the performance of R14A and propane in a direct and indirect expansion heat pumps. Now we'll focus just on the first activity. So basically, in the lab, we have an experimental setup that mimics a brine-to-water heat pump. Here you can recognize in black the refrigerant loop, the classical one, the compressor, condenser, liquid receiver, expansion valve, evaporator, and so on. And two secondary fluids loop, the hot water loop in red and the cold water plus ethylene glycol mixture loop in blue. These two secondary fluid loops are used to set the mass flow rate and the temperatures of the two secondary fluids that flow through the condenser and the evaporator in order to run the test. To characterize the heat pump, we run 25 different tests for each refrigerant. Tests are a matrix of the experimental conditions is shown here. On the we run tests spanning from -5 to 15 Celsius degree as the water ethylene glycol mixture at the outlet of the evaporator, and from 35 to 75 Celsius degree as the water temperature at condenser outlet. All tests are carried out setting the superheating to a constant value, which is 5 Celsius degree, whereas the subcooling is free to vary. To run the test, we had to identify the mass flow rate of water and ethylene glycol that flows through the condenser and the evaporator. And we did it setting some reference condition, which is the red dot. In these 5 different reference conditions, we identify the mass flow rate, the mass flow rates, sorry, that lead to a temperature difference of the secondary fluid equal to 5 Celsius degree. Once these two mass flow rates are identified, we kept them constant in order to run the test at constant water temperature at condenser outlet. As an example, in this row, we have the same water flow rate in the condenser and the same water ethylene glycol flow rate in the evaporator. And then when we go in different set of tests, we change them. Just to give you an example of the results we obtain, here are 2 different figures. On the left hand side, the capacity, the condenser capacity, or on the right hand side, the COP. On the x-axis of both figures, we can find the temperature of the water at condenser outlet, and these 2 figures refer to a water ethylene glycol temperature at evaporator outlet equal to 5 Celsius degree. As you can see, we compare 5 different refrigerants, R134A, which is the baseline, then the 2 HFOs, the 1234ZE and the YF, and then the 2 mixtures of R134A and the 2 HFOs, basically R450A and 513A. As you can see, we can say that more or less the R513A is the alternative refrigerant that provides the closest capacity to the baseline, to the R134A, whatever is the temperature at of the water at condenser outlet. Whereas on the other side, the 1234ZE is the refrigerant which is most penalized, meaning that the capacity, the heating capacity of the heat pump reduces by around 20%. If we look at the COP, so the figure on the right, we see that the refrigerants, the performance of the refrigerants is very similar. The refrigerant that has the closest performance to the baseline is the R450A, so the green bar, whereas the refrigerant that has the lowest performance, even if the difference is not very high, is the 1234YF. And that's all for the performance at the system level in lab environment. Now, Sergio for the last research activity and then the conclusions.
Okay, as I said before, can you put the next slide. Thank you. Okay, so as I said before, the second project completed in the last year was an European project called Geoforcivic, which had the aim to study geothermal heat pumps, shallow geothermal systems, for heating and cooling in the retrofitting of existing and historic building. Within the project, we studied both the heat pumps as a system to produce cooling and heating, but also the drilling technology to create the ground heat exchange. Anyway, as refer our group, we were involved in the study of the alternative refrigerant, low-GWP refrigerants to be applied in the heat pump and the evaluation of their performance. Next slide, thank you. So the first step of the project was to install in a demo site here at the CNR in Padua an heat pump with an internal regenerator that was totally monitored, both to the refrigerant side and the secondary fluids side, to have a possibility to evaluate the behavior of the heat pump and to evaluate the performance by measuring the most important thermodynamic parameters. So the heat pumps was endowed with thermo resistances to measure the temperature, and with a sensor of pressure in the main points of the heat pump. And also we used a mass flow rate Coriolis flow meter to evaluate the flow rates of the refrigerants inside the heat pump. So next slide, just to have an idea about the reliability of the monitoring system. Here you can see the first principle energy balance at the refrigerant side, and you can see that in principle the balance should be 0 between the power at the condenser, the sum of the power at the evaporator and the compressor. Here we have actually an imbalance of more or less 2%. That it is absolutely acceptable from the practical point of view. So the monitoring system was quite good. Next slide, please. So we measured the performance of the system working with R454B for several months. And as you can see, the COP was around ranged between 4 and 6.5. That was quite good performance. Anyway, the idea was to compare the results obtained with this refrigerant with those obtained with isobutane that was selected as the very low GWP refrigerant for the long-term substitution of HFCs. This evaluation is still in progress, and in the next months we will have an idea about the comparison between the two fluids. Okay, thank you. So to conclude the part regarding the Italian contribution to the study of heat pumps, we can say that we performed both basic and applied research studying the thermophysical properties and heat transfer properties of the refrigerants and their application in heat pumps. we investigated several low-GWP refrigerants, and they are still under investigation. The main conclusion we can say, but it is quite well known in the research field, is that in our research field is that even if we have several alternative to low-GWP alternative to substitute the present refrigerants, it is difficult to find a single solution. It is necessary in some way to identify a proper alternative for each application of heat pump, considering not only the thermodynamic features, but also safety aspect and environmental aspects of the single refrigerants. Thank you. I have concluded. We have concluded, and we are open to your question.
All right. Thank you very much. So that Italian report is just made. If you have any question again, please use the trading box. Meanwhile, there's one comment from the Dr. Frank Lipke. It's about applying the plate type internal heat exchangers to get a potential benefit. What I'm thinking is depending upon the walking fluid, some walking fluid has a higher benefit by using internal heat exchangers. However, some fluid is not. So depending upon the choice of the fluid, internal heat exchanger could be beneficial or not. And for the most of the fluid, yes, it is beneficial. And again, there are several types of the internal heat exchangers available. The simple geometry could be the tube-in-tube type, or it can be a microchannel to microchannel blades together, or as suggested, plate type heat exchanger can be also used. Amongst the pre-enter, if you have any answer to Dr. Frank, please answer to that as well using the chatting box. Right, thank you. All right, our next one is the Swedish country report. Presentation will be made by Professor Bejon Palm from Royal Institute of Technologies. All right.
Yes, Yunho, how are you doing in time? Should I stick to 10 minutes or?
Yeah, we are a little bit behind the schedule, but you can use as planned.
Okay. So I hope you can see my screen now.
Yes, it looks good.
Yeah, very good. So just to start by saying that what we have been reporting in our country report is several research projects which have been running in parallel, all related, of course, to low-GWP refrigerants. So it's not one or two or three specific projects, but several projects which have been running in Sweden. So I cannot go into any details in many of them, but I will mention some about. Oops. Yeah, and sorry. So and I also have in my presentation some market development and outlooks for the future. We will see if I have time for that. And also, I would like to say that with this report from Sweden has been done in cooperation between us at KTH Royal Institute of Technology and also RISE Research Institute of Sweden. So research highlights. I would like to start by saying that we have been working on low-GWP refrigerants since 1995, and I just listed a lot of different projects which we have been running since 1995. Or between 1995 and 2018 here. And you will see that all of them are actually topics which are still being researched, and some which have not been researched so much. For example, domestic ammonia heat pumps and domestic CO2 heat pumps have not been covered here in these reports. And just to indicate, one refrigerant which we have tested long ago is cyclopropane. We have a refrigerator which has been operating in our coffee room now since we did those tests for 25 years. And this is a refrigerant which you have, I think, is overlooked in a lot of ways. It's a good refrigerant and deserves to be investigated more. And of course, we've been working with safety with flammable refrigerants. This is just the front page of one of our earlier reports. Yeah, and this is an early prototype of a low charge propane heat pump. And you can see it's a liquid to liquid heat pump with a automotive type compressors. And I'll come back to this a little bit later, but this is research which was done long before this Annex 54 started. We've also been part of several EU projects and worked with some of the participants in this seminar also in these projects. Some talk about the research on charge reduction, which have been ongoing during the last few years. One project is called EcoPack. And in this project, we tried to design a small economizer heat pump, as we call it, a heat pump which is using the subcooling of a larger heat pump as a heat source. And you can see the scheme to the right here. So the idea is to be able to produce sanitary hot water at a higher temperature than the condensing temperature of the larger heat pump. And this, we used isobutane as a refrigerant in this case. And we showed that it was possible to provide up to 12 kilowatt of heating with a charge of less than 150 grams of isobutane. Some interesting parts of this, as we used once again a compressor which was originally designed for automotive, but this one is actually used for stationary applications, or built for stationary applications, I should say. We had, as you saw in the scheme, a internal heat exchanger, and of course this is a critical component if you want to decrease charge. So we had to build prototypes as we didn't find anything on the market which was suitable for this, using microchannels, as you can see. In another project called ProPack, which was in a way an extension of the EcoPack project, we instead looked at the air-to-air split air conditioner system. So the goal was here to design a 3.5 kilowatt cooling capacity air-to-air split system with 150 grams of propane in this case. And to the left there, you see a small heat exchanger, which is the prototype internal heat exchanger, which we designed for this project. And some details of this, I mean, one of the difficult parts is to reduce, well, we used microchannels, of course, to reduce the charge, but the headers is one big problem. And you can see how the parts of the tubes were cut in the headers here to not to have a pool of liquid at the top of the condenser in this case. And we used vertical tubes, as you can see. Let's see, next we have a project ongoing on high temperature heat pumps. The focus right now is on oils, which oils to use with different types of refrigerants. We have the rig, which you can see down to the left. It's built to be able to run at different capacities and with different refrigerants. We are targeting temperatures up to 120 degrees, as it looks like now, both hydrocarbons and synthetics. So this is a project which is still running. And another project which is still running is more about fundamental studies on boiling in flat channels. So to reduce charge, we need to have flat channels. And in this case, we use a channel in between a very thin metal foil, which is heated, and a back wall, so to say, a glass wall. So we can look at the flow through the glass wall from one side, and we can look at the temperatures of the heated thin foil at the other side. So therefore, thereby we can see where is it cooling good and where is it not good. And we're hoping to be able to learn something about where evaporation takes place in this way under flat bubbles in a flat channel. Ongoing work. Transcritical carbon dioxide systems is the standard solution now in Northern Europe. Scandinavia in particular. And of course, there is a lot to do here to use also the hot side of the system. So this is often combined with heating and cooling of heating using gas coolers or condensers or these superheaters in different combinations. So there's a lot to do here to make these systems more energy efficient. Well, yes, we also did a market investigation here about refrigerants for low GWP refrigerants in the Swedish market. And dividing this up into different types of systems, air-to-air heat pumps, there is no production in Sweden, and the ones imported are using R32. Air-to-water heat pumps, split type usually, or split type air-to-water heat pumps typically use R32. Many producers in Europe and the one in Sweden. Air-to-water heat pumps, monoblocks, there are many producers in Europe and one in Sweden, and many are in Europe and one in Sweden are using propane, I should say. Brine or water to water heat pumps. This is a very common type in Sweden. Manufacturers, two manufacturers offer synthetic low GWP refrigerants, as you can see. And heat pumps with low charge of propane are under development from several manufacturers, both in Sweden and in the rest of Europe. When it comes to exhaust air heat pumps, there are at least 3 manufacturers in Sweden, and propane has been used in these type of systems since the 1990s. R32 is also used, as well as R407C to some extent. We'll come back to that later. Yes. When it comes to site-built systems, CO2 and ammonia are actually the preferred refrigerants, I would say. And if we look at larger pre-manufactured systems, propane is offered by at least 2 manufacturers. For 513 is used by 1 manufacturer, and R32 is used by 1 manufacturer. So there is a different refrigerant to choose from here, but propane is one option. I just want to show you 2 case studies here. One is one company selling a product they call E-Box. So this is a propane heat pump for heating multifamily buildings, and it's built into a container or 2 containers. So these are just placed in close to the building which is to be heated. So it's very easy and simple installation. You can hide the containers with a small house, and heat is extracted from the ground. Ground is a heat source. Very simple installation, so short installation time. The second case study is this CO2 system for heating and cooling. So this is in a supermarket having a large surface area of 11,000 square meters. And the system is also heating 5,000 square meter buildings around this supermarket. And it's using 20 boreholes, each 220 meters deep. And also you get passive air conditioning through the borehole field. So combining supermarket refrigeration with sort of a geothermal heat pump, that's the novelty of this system. I think I would skip the last one. Some design recommendations for low charge, which we have agreed on, so to say, in Sweden. So, I mean, charge reduction should not be achieved by decreasing the heat transfer areas. I think this is very important. We need good performance. All lines should be as short as possible, in particular, important to have a short liquid line. This is obvious, I would say. And we think that flat channel heat exchangers should be used. For example, extruded aluminum multi-channel tubes or plate heat exchangers with small pressing depths. So this is something we've been working on, development of heat exchangers with small charge. And one problem with the heat exchangers is always the headers, because headers could take actually as large charge as the rest of the heat exchangers if you're not careful. And of course, if we use typical standard compressors, there is a large charge of oil which will absorb a lot of refrigerant. And this has to be handled in some way if you want to decrease the charge. And another notion on this, on these 2 graphs, you can see the specific charge versus the seasonal COP. And the red crosses here are for different products on the market with using R290. So this is not only in Sweden, but in the European market. And what I want to point out here is that it is not a clear connection between the seasonal COP and the specific charge. So it's possible to build systems with low specific charge and still with high seasonal COP. This is true both for air-water heat pumps and for liquid water heat pumps. Yeah, some of you are not from Europe, so I just want to point out that in Europe we have the F-gas directive, and F-gases are phased out. HFCs are phased out to 2050, and also some types of products are going to be forbidden. So by 2035, systems with lower capacity than 12 kilowatt will not be allowed using any types of F-gases, including HFOs. So with some possible exceptions. So this means that at the same time, we know that there is a discussion about PFAS. So all the synthetics are on their way out, you could say, in Europe. And at the same time, EU has decided to phase out fossil fuels. So this means that 60 million gas heaters or even more will have to be replaced. So there is an enormous market for heat pumps in Europe. Just as, and of course, is phasing out both F-gases and increasing the number of heat pumps in this way is a challenge for Europe. You can see the market development here. 2023 is not continuing to increase. It's rather decrease compared to 22, but still we believe that there will be a substantial increase in the near future. So yeah. The market is different. I will skip this actually. When it comes to the expectations of heat pump producers and importers in Sweden, we have asked them how they think the market will develop. And as you can see, almost all of them have answered very high or moderately high growth over the market. Very few things of a low market in the future. So, and this is natural, I think, with the background we saw before. We have also asked installers and asked them to estimate the distribution of type of refrigerant in different types of systems. And if we start looking at the green parts of these circles here, this is refrigerant R290 propane. And you can see that propane is not used much in air, water, or air-to-air heat pumps or liquid water heat pumps. But in exhaust air heat pumps, it's estimated that it's about 1/3 of the heat pumps using propane. If we look at the blue part, we can see that this is R32, which is dominating in air-water heat pumps and air-to-air heat pumps, but has a smaller share of the other types. And we can see also the orange here for R410 is still used quite a lot in air-water, liquid water heat pumps. And finally, we can see that R134A is also still used in exhaust air heat pumps to relatively large extent. We also looked about the study of market opportunities for low-GWP refrigerants, asked 5 manufacturers about their opinion. And some conclusions on this was that all expect a growing market demand for low-GWP products. And asking about the barriers, medium-term barriers for low-GWP refrigerants, these were the answers. Differences in regulations between countries is one problem. Safety issues related to flammability is another. Availability of trained installers and technicians is the third. And there are major growth opportunities only. When we asked about that, the responses were only hydrocarbons, carbon dioxide, and ammonia. So no other fluids are expected to grow, asking these manufacturers. Thank you for your attention. That was a very quick version of my presentation, actually, but I guess we're short of time.
All right, thank you very much. If you have any questions, please again use the chatting box. Meanwhile, there's one question from Teoru to Luca on the the system level work. Question was why R290 was not part of the study. So Luca, please prepare the answers, and if you can, please answer through the chatting box as well. All right, now let's move on to the next country report for the USA. Presentation will be given by Dr. Lei Gao. All right, slide looks great. Yeah, please go ahead. Lei, I cannot hear you. Are you muted? Please unmute it if so.
Oh, sorry.
Now I
yeah,
can hear you. But now slide is gone. Okay, slide is back. All right, please go ahead.
Okay. Yeah, good morning and good afternoon, everyone. Thanks for attending this seminar. I'm Lei Gao, a postdoc at University of Maryland. I work with Professor Yunho Hwang, and we will give a brief update for the multiple research project led by multiple US institute. The left side table highlights the sample projects in the past few years led by this institute, shows in the left, in the right side. This project including alternative refrigerant usage, standard policies, some case study like our 15.1.6a novel system design, including unitary system and saturation heat pump system, and also including heat exchanger design optimization and last but not least, LCCP research work. So this presentation will then divided based on the target task. The very first task is about review of the state of art. The first below figure shows the comparison between different refrigerant and GWP versus refrigerant density or pressure. It is observed that the majority of low GWP candidates are A2L type and with mild flammability. Recent development are focusing on refrigerant mixture development. Most mixture use non-flammable composite to compress the flammability of R32. Some candidates sacrifice some degree of performance. That being said, some of the mixture are still A2L refrigerant. Therefore, safety research on them are still necessary. And second, other promising candidates are most natural refrigerant like CO2, but it still requires significant overhaul of the entire system design. Therefore, it is less attractive than the other A1 candidates, such as R4166A, which require much fewer system change. Some of the A3 refrigerant are being considered and started, especially in China. However, they are far away from commercialization due to safety concern. B-type refrigerant like ammonia have not been actively discussed in the residential sectors. And this table shows a launch project related to low GWP refrigerant in the US. This project were developed as a result of survey of safety standard. I'm sorry, this table seems a little bit small, but they are prioritized among other identified research needs and considered as a high priority project by a group of experts, including industrial experts, a major safety standard committee chair and the members, and some representatives from the US DOE, Environment Protection Agency, and National Institute of Standard and Technology. This slide shows the code adoption process of a new refrigerant in US, started with refrigerant safety classification in ASHRAE Standard 34 and the EPA SNAP program approval. The next step is to ensure refrigerant usage complied with safety standard, notably the ASHRAE Standard 15 and the UL 16335. Following that, it is to be adopted by the relevant building code, state, and the local code. And here, this table shows the different refrigerant category for the different lower GWP alternative for thermodynamic performance evaluation, which is comparable in terms of a different application for current baseline design. The short term here represent for the refrigerant determined as the refrigerant that are available and are being offered by at least one commercial producer. And the long-term alternative refrigerant are defined as those which are listed in ASHRAE standard 134 and have been potential to replace the baseline refrigerant with similar performance but not being commercialized. The second part is about the case study and some design guideline. The very first design is a unitary system that can enable safe flammable refrigerant usage while ensuring performance advantage over R14A. And the left side shows the system diagram, and the right side figure shows the system COP performance evaluation. The simulation result shows the system performance along with ambient dry bulb temperature change. And different color of the line represent for different cycle options, including single stage, two stage, and with different refrigerant like R32 and R290, and the baseline R14A. It is observed that the system COP decreased with ambient temperature increase. In addition, the two-stage cycle has better performance than the single stage, which has around 1% at the 35 degrees Celsius ambient temperature. And in terms of the alternative refrigerant investigation, the very low GWP refrigerant R516A has shown promising results compared with R134A. In medium pressure chiller application, in this work, the R516A has been evaluated in terms of the L2 water source heat pump. And when the left side shows that when the compressor performance of the R516A was compared to that R134A with same motor design, both the capacity and the ER for the cooling and the COP under the heating mode, that will be slightly lower than R134A. And in terms of the compressor operation speed, the R516A shows nearly identical speed with the baseline design, and the capacity efficiency performance of the R516A in the heating mode was closer to their baseline, which become critical with the choice of optimizing the product design to either cooling or heating, depending on the primary application driver. In terms of a discharge temperature, shows on the right side two figures. R516A shows approximately 6 Kelvin lower discharge temperature at the cooling condition and 6 Kelvin lower at the specific heating condition compared to that of the baseline. And this make the new system design dropping with 516A more favorable in high temperature lift condition. Here is another novel system design. The left side figure indicate a heat pump system operate under for the high temperature heat pump application with 100 degrees Celsius evaporating temperature and 100 Kelvin temperature lift. The red line, solid line in the figure represent for a conventional single-stage heat pump system design. When compared with typical compression ratio of the single-stage mechanical gas compressor, that would be around 2.5 to 4. However, the required total pressure for such high temperature heat pump, like 100 degree Kelvin, that would be over 12 in terms of the compression ratio. So multiple stage compressor will implement. However, in this project, University of Maryland proposed a set of techniques that aim to boost both COP and the system capacity for both for the industrial application. And the saturation cycle with 2 injection alone will lead to the heating COP of 16.7% of counter efficiency theoretically with low GWP refrigerant. And this work is led by University of Maryland. They developed the heat exchanger optimization framework showed on the left side, which is called approximate assisted optimization framework that will involve automatic computation of fluid dynamic and FEA simulation and Kringing model and optimization with multi-objective genetic algorithm. And the right side shows the final optimized heat exchanger in the format of fin tube heat exchanger and finish heat exchanger. This figure shows, this table shows the performance comparison by utilizing this framework. And in terms of the different refrigerant, R14A, the next refrigerant replacement, R32, R415-4B, and a low GWP refrigerant, including natural refrigerant and supercritical carbon dioxide, and the application expand from the AC heat pump gas cooler. This heat exchange consistently meet the design target compared with the commercial available products, and the high performance heat exchanger for stationary system with the weight reduction more than 20% and more than 20% of volume reduction, as well as the 25% of refrigerant charge reduction. So the last part is shows the LCCP investigation. Here, this figure shows the LCCP breakdown in terms of the direct and indirect in subsector, and this figure shows the LCCP result in different regions for R14A as an example. And from the figure, we can find that LCCP for Basel and Calax has very small value, and the reason is that the power factor for Sweden and Switzerland is very small. Only for the 2 regions, the annual leakage is the major factor for the LCCP. And for all other regions, the annual energy consumption is the major factor for the LCCP value. And here are some highlights for the LCCP review. So in conclusion, the major factor in terms of the annual energy consumption and the refrigerant leakage are the major contributor to LCCP. In high efficient factor country, the energy efficient is crucial, while in low GF country, leakage play a significant role. And the weather data discrepancy also play an important role there. And in terms of a low refrigerant, GWP refrigerant, the effective in reduction emission, their performance vary by region. R290 shows the most promising in reducing the LCCP. especially in low-GWP country. And there list some future work. We'll evaluate alternative refrigerant and including refrigerant like 416.6A, and we were including more regions to compile to compose more comprehensive global perspectives. And we will also study the relationship between LCCP and the cost to optimize the performance based on the economic consideration. Yeah, we composed some outlook for 2030, and in terms of the research direction, including the evaluation of different refrigerant, the flammable refrigerant, and also we will explore some natural refrigerant and explore the zero or near zero GWP refrigerant. And in terms of the regulation, we will consider globally the low-GWP refrigerant adoption and the standard policy, the safety standard such as the ASHRAE 15 and the UL standard. And in terms of a technology advancement, we will still looking for the innovative system design and incorporate the optimized techniques into this system design. Thank you guys for your attention.
All right, thank you very much. With that, we all presented about the heat pump with low global warming potential refrigerant. Research is conducted over the past 5 years. If you have any questions, again, please let us know. So meanwhile, we will be preparing the final report. All the presentation slides as well as the final report will be available through the IEA HPT later on. So again, here are the contact information. If you have any questions about the Annex 54, please let me know. My email is yhhwang@umd.edu. And also later on for the final report publications, then please contact Dr. Metkel Yebiyo. His email is metkel.yebiyo@ri.se. With that, I'd like to conclude our webinar, and also we appreciate all the speakers as well as the attendees. All right, thank you very much for your participation. Then I wish you have a good night or good evening or good morning, depending upon where you are. All right, thank you very much.
Thank you. Bye.
Thank you.
Okay. Yeah. Bye-bye.
Bye.
Thank you. Bye.
Thank you. Bye. Bye.